Greetings and welcome to a new video about Miller's theorem. In this example we will discuss how we can apply the Miller's theorem on a voltage amplifier having a capacitive feedback. So we will see how that will be affecting our frequency response of the voltage amplifier. Of course we will see everything clearly step by step in our calculations and verify this in SPI simulations. First we start with the non-ideal amplifier with the capacitive feedback. This is the circuit we will use. You see here the capacitive feedback between the nodes here. And we also have the model of our voltage amplifier. In addition, you see here the source, Vs, and also the source resistance of that input. We have also the load resistance here. Our objective is using the Miller's theorem to determine the transfer function of the closed loop voltage gain in the Laplace domain, given here by T is equal to the output voltage divided by the source voltage. Now, before we discuss in detail, let's first go through the voltage amplifier model. This is the model actually which you see here, and that is given here in the dashed part of the circuit. You have here the parameters. These are the input resistance, Ri, the output resistance, Ro, and we have also the open circuit voltage gain, A0. That is the gain when you have an open connection between these two nodes of your circuit. In an ideal voltage amplifier, we have the input resistance that is actually infinite. That means this is practically open. The output resistance is actually 0, so that is then practically a short. And the open circuit voltage gain A0 is infinite. So we have here an infinite gain. Okay, so if we now use the Miller's theorem as we have done it in the feedback resistance part of the voltage amplifier, you convert actually this original circuit in this equivalent circuit. You see here two capacitances, you see in Miller and the C out Miller from one capacitor. So we transform this into two separate capacitances, input capacitor and the output capacitor. That will definitely determine our frequency response. So how to work this out in detail, that is actually the objective of this example. Okay, let's bring it here and then continue. First, we define the following parameter. I call this the open feedback voltage gain. That is the voltage gain of our circuit from the nodes where we have the connection of our feedback element. And then we also disable or make this CF open. And if I now define here two nodes, node X and Y, and also for our equivalent circuit we have determined, we can determine the gain going from node X to node Y. That is also the connection of our feedback element. So the gain is now here determined given by the AXY, which is then the voltage at the node Y divided by the voltage at node X. And if you look at the circuit, it is actually at this voltage node you have actually VI or Vx, and this node you have actually the voltage A0 times VI. That is actually this ratio, so output divided by the input, this part. And then you also go from this part to that part, that is actually Vy divided by this A0 times VI. Well, if we convert that now to the form that we can use in our calculations, because this is just A0 and this is the voltage divider rule, the second part. So if I now look at that, the red part is just A0 and the blue part here is just the voltage divider rule, RL, load resistance, divided by the summation of the RO and the RL. So this is now the expression of our open feedback voltage gain we will use shortly. Now the Miller capacitance, the input part, is then calculated using this open feedback voltage gain expression, and that is given here. So you have here the CF that was converted to, of course, the C in Miller and also C out Miller, and that will be then determined using this open feedback voltage gain. Similarly for the Miller output capacitance, similarly actually also what we have done, having a feedback resistance in the other video. So when you substitute here the values, for example in this case, we take these values for our model of the operational amplifier or our voltage gains, or Ri, Ro, and A0, source, load, and the feedback capacitor is shown here. So if I now take that all here and then substitute in this formula of the open feedback voltage, can I get here minus 90.91. Now substitute that in the formula for the C in Miller, you get here 919.1 picofarads. So you actually have increased your capacitance from 10 picofarads, because it was original, to 919 picofarads. So this is a quite improvement or increase in our capacitance. Similarly, we can substitute here the formula in the formula for the Cout Miller, and there you get here a value of 10.11 picofarad. This is almost the same as the original CF because you divide here by the gain. If the gain is large, then the Cout Miller is almost the same as CF, but the C Miller is much larger than the CF. So that will be, of course, having an effect on our frequency response we will see shortly. How about the closed loop voltage gain? Well, that was T given in the statement here in the objective. And we can now define here the parallel combination of the capacitance C in Miller and the resistance Ri of our voltage amplifier model. And we call this, for example, Zx. So that's the reactance, because we have to talk about the reactance of a reactive component in parallel with Ri. Similarly, for the output part, we have the Cout Miller and the RL here in parallel. So we have to look at the reactance of the Cout Miller and the RL, and that I call Zy here. So I have two impedances, Zx and Zy, and I can see actually here now the voltage divider rule again, what I can apply, and I can say at this node I see then Zx over Rs plus Zx, that's the voltage divider, and then I go from here to there, and then from there to there output again I apply here the voltage divider rule. So in total, you see first there's the input voltage division from the Vs all the way to this node. That's Zx over Rs plus Zx, and then times A0, because that's just from this node to that node, jumping actually using this voltage controlled voltage source. And from there to the output again, you have a Zy over Ro plus Zy. Alright. So we have now the values of our open feedback voltage gain for this specific set of values, and we have the Miller input and Miller output capacitance, and we have the closed loop voltage gain transfer function. Well, we have to, of course, work it out in more detail what this Zx and Zy is, so we can use the reactance formula for our capacitance, and it's 1 over the S times the capacitance, in this case C Miller, so we specifically also put that here. And now we know that two elements in parallel, meaning the product over the summation, that's the formula. If you work it out, you get actually this result, and similarly for Zy, and you get this result. So we have now the two expressions for Zx and Zy. We can now substitute in the formula for our closed loop voltage gain T. So these are now given here in this example. Okay, so we have now the closed loop voltage gain expression and also the Zx and Zy. So we can continue and then substitute that in here. You see how actually in here I have put here the Zx, and also here you have the Zx, so you have to also put it there. And you also have a Zy and Zy here, so that means you have a Zy and Zy there. So what we can do, we can now continue and simplify this expression by multiplying this part by 1 plus SRI C in Miller, and also of course the denominator, just to actually get rid of these fractions in the fraction. That's of course quite annoying. I will also do that for this part, so I will also multiply in this part the numerator and denominator by 1 plus SRL Cout Miller. And this A0 is of course a constant, so I can also bring it in front. So that's all what I do. So you see here, Ri is actually only left here in the numerator, and here the Rs will be multiplied by this term. And now you can also work out the parentheses, similarly of course also there, and also bring the A0 in front. You have now here the expression as we wanted. Now we can actually group the constants, so the terms which are real, so these are the Rs and Ri, and also for here Ro and RL, and we can keep the terms where we have the parameter S Laplace parameter, which is a frequency dependent parameter, and then we can come up to this point. So this expression is already in a form that we can use easily, but it is a little bit better if we continue and then make the 1 plus S times a specific value, which we call later the time constant. So what I do, I will divide by the Rs plus Ri here, also of course there, and also of course here, and I will divide here in this part by the Ro plus RL, and also here and also there. That means you get here a 1 and also here a 1, and the result will be here. You can see that up, and then there will be actually here the division, and you get a 1 plus S times some product, and also again S times some product here. And you see actually the parallel combination of the Rs and Ri is actually here appearing, and also here Ro and RL. Well, we can write this in a more convenient and more compact way by defining actually what we call the time constant tau in and tau out. That is the input and the output time constants. So here we can say that tau in is the product of this and the capacitor C in Miller, and the tau out is the product of this parallel combination of the resistances and the C out Miller. Now we have again this circuit, and that is actually what we have gained after this Miller's theorem. We come up actually to this transfer function where you see two poles. Okay, getting to the next step, and very important note actually here. The Miller's theorem actually requires that the floating impedance or floating element here and the voltage gain we have calculated will be at the same frequency. However, we use the DC gain because you know from the open feedback voltage gain AXY, we have looked at the situation where the capacitance was gone, so we are not considering actually all the frequencies, just DC. So this presence of the CF will definitely lower the gain at higher frequencies. So we know that because the higher the frequency, the lower the reactance of this one, so it will be coming closer and closer to the short. So this gives rise actually to the point where we can say that the Miller's theorem is turning into a Miller's approximation. And due to this approximation, the circuit actually exhibits two poles while we have just one capacitor. That's interesting. So that's also the shortcoming of this Miller theorem using on this circuit. In addition, direct input to output transfer, so from here to there, is also not considered and not taken into account. We will have a zero frequency. We will see that shortly also in our simulations in the Bode plot, and that is also not taken into account by Miller's theorem. So again, that's why it's called Miller's approximation. This is an important note. Before we continue, we will see some deviations from the simulations value in our calculations. Okay, let's bring it here and then continue. This was our circuit, and again we convert that here in this equivalent circuit, having a C in Miller and C out Miller. And again, using the values here, we can calculate now, again, our capacitances C Miller and C out Miller in our open feedback voltage chain as we have done it before. Now we can use that, we can use the values of C in Miller and C out Miller and the resistances to calculate the time constants tau in and tau out. This is here, you see here the value of 9.182 microseconds. And the second, the tau out is 919.1 picoseconds. So this is much smaller actually than this one. This will of course have some meaning. Later we will see that what it all means, because the time constant will also reflect which pole will be dominating. Well, about the poles, you have, because of the time constant, you can reflect that to the poles. Because at the input, you have the input pole frequency, what we call the pole frequency, and you have also the output pole frequency. And the input pole frequency is the inverse of our time constant, so 1 over the tau in. So you just do 1 over that. You get here 108.9 kiloradians, so 10 to the power 3 radians per second. How about omega out? Well, 1 over the tau out, that will be then 1.088 gigaradians per second, so that's 10 to the power 9. You see this is much larger than that one. And that will of course create some approximation in our estimation of our cutoff frequency and also the bandwidth. So we can use that fact that this is much smaller than that one. But we can also use an estimation of our cutoff frequency, because there is of course an exact formula, but it's of course a little bit complicated and also not really design friendly. So we can use an estimation of a cutoff frequency for this case where we have only the poles, and we can use that by using the formula 1 over the square root of each of these pole frequencies squared, but of course also taking as an inverse and then add them up. That's actually the formula. If you do that, you will come up actually to this value, which is the smallest. So you can also examine this for yourself by using two values, which are, for example, this is, let's say 10, this is, let's say 10,000, and you will end up here at almost 10. So you get here on omega c, which is almost the same as, in this case, exact same because of the rounding of errors, omega in. And if I now look at the cutoff frequency in hertz, you just divide by 2 pi, you get here 17.33 kilohertz. So again, the smallest pole frequency or the largest time constant, that's the inverse, will determine, in this case, the upper cutoff frequency. Okay, how about a DC gain? Well, We know that the DC gain can be calculated when you have the capacitances open, because DC meaning the capacitors are open. So you can say it is the voltage divider rule, so Ri over Rs plus Ri, that's actually this part. You have also here the RL and the RO, and again the voltage divider rule between these two resistances, and you have the A0 going from this node to that node. That's all shown here. Substitute the values here, you get here minus 90.818, and that will be then in dBs, 39.16 dB. We can also present our transfer function now using the values for the DC gain. So this is actually the product here and the numerators. And we also have a time constant, so we can also substitute that in here, and you see the result here. Okay, let's now verify our results in the simulations. So the simulation results for this part of the example where we have the values as we have it. And this is our Tina TI SPICE simulation circuit, and this is the Bode plot for the gain. You see here the voltage control voltage source element having a gain of minus 100, and also the other parameters we have selected for our example. This was our circuit and it was our transfer function. And here you see the calculations for this example where we have a DC gain of 39.16 dB, and also what we have here. And we have the cutoff frequency we have calculated was 17.33 kilohertz, which is also what we see here. So these are of course very nice results. In addition, what we do not have calculated, what we do not have seen using the Miller's theorem, is that we have a high frequency gain, almost minus 80 here dB. And we have also the gain at that value where you go up by 3.01 dB, which is our zero frequency. Because if this was a pole frequency and then eventually the higher frequency will actually go down, 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 down. But at some point it will actually flatten down because there's a zero, so it will compensate that effect of the pole. So you see that actually the action here. There's also one pole and one zero here. That is also what you see here. This is not taken into account, not seen by the Miller's theorem. That's why it's called also the Miller's approximation for that matter. Okay, now we will now ask the following question. What will now happen if we adjust the values, the component values in our circuit? Is Miller's approximation or Miller's theorem still good enough? So this was a circuit, bringing up, and here are some cases. I have here put the parameters like open circuit voltage gain, input resistance, output resistance. So this part is the model of our operational amplifier or the voltage amplifier. The source resistance and the load. And here I have the feedback resistance and other parameters we have seen in our examples. I have 5 cases. I will look at the first 3 where I have changed the feedback capacitance from 10, 100 and 1000 picofarad. That's actually what you see here. Well, that will of course change something. Now you see here all the way all down, which is the estimated upper cutoff frequency in hertz. That is now here 1.733 10 to the power 4, so that's the 17.33 kilohertz, and then 1.733 kilohertz, and then again 10 times smaller, 173.3 hertz. So the larger the feedback capacitor, so 10 times larger, will make also the cutoff frequency 10 times smaller. That's the effect actually from our calculations. Is that true? From our simulation results, we can bring it up. And you see here the blue one, which is the original situation, where we have the CF of 10 pico. The pink one is for 100 pico, and for the CF in the red one is for 1000 pico or 1 nano. You see in all cases that the DC gain is 39.16 dB, so that's not changed. But we have a change, so it will shift to the left when the capacitor's value will go up. You also see that actually in the time constant, because the time constant will also go up by this factor, that will also reflect in the cutoff frequency. Okay, that's all nice, so you can also see that the effect of the capacitor will have an effect on the cutoff frequency directly. Now there's also another case, case 4. In this case I will make a drastic change in my source resistance. Practically I want to make it 0, but I will look at the situation where it is non-zero, but very close to 0, so 1 milliohm. So it was before 10 kilo ohm, so 10,000, now I have just 0.001. This can be of course happening that you have a source which is a very small or almost zero source resistance. What will then happen to the situation? Well, from our calculations you see actually that our cutoff frequency should be then 1.73 times 10 to the power 8, which is actually here if you do the math, if you convert that to the megahertz, it will be then 173.2 megahertz. Let's check that again in the simulation. So just focusing on the case 4 in this case. So you see here again the circuit, but now the RS is 1 milliohm. That's the only change actually in this case 4. The rest are exact same as in case 1. And we see here the DC gain has increased slightly to 39.17 dB. And our cutoff frequency here, that's also what we of course can calculate, by the way, by using the formula, and you get here the value of the DC gain. And you convert that to dBs, you get indeed as we have seen it in the simulations here. The cutoff frequency is given as 174.9 megahertz, and we have here 173.2 megahertz. So you can say, well, how much difference is that? Now if you look at, if you compare that here, it is just a small difference, maybe 1%, and that is good enough actually for most practical purposes. But there is of course a slight change here and slight difference. That's again because of this Miller's approximation. What we also see again our zero frequency and our high frequency gain we do not take into account in the Miller's approximation for this situation. So if we can say it's still good enough, just looking at our upper cutoff frequency and our DC gain. We can also look at a situation which is an extreme situation, case 5, where we keep the source resistance as 1 milliohm. And I reduce my load resistance from 1 kilo to 1 ohm. So there's a very small resistance now. What happens then? Well, if I look at that, the input time constant now is quite small, very, very small. It was 1.99 times 10 to the power minus 14. And the output time constant is now much larger. So it is actually 1000 times larger. That means the smaller time constant, the closer actually the pole is in the complex plane to the vertical axis. If you look at that in that way, you can also see that in the pole frequency, because now the omega in is much, much larger than the omega out, which is our output pole frequency. That will determine then definitely also our pole frequency and our cutoff frequency in the estimation. So you can see the estimated upper cutoff frequency omega c is in this case exact same as the omega out, and the omega in is actually not at all in the picture. Now looking at the part here where we see the RS is 1 milliohm and RL is 1 ohm. Again, the other parameters are exactly as in the beginning in the case 1. You see indeed the DC gain, we can calculate that. It will be then minus 0.99 by actually substituting the values, and also the situation for case 5. And if you convert that, you get here a DC gain of minus 86.43 millidBs, which is also what we see here. And we also have a high frequency gain, which is in this case minus 17.44 dB. The situation is actually quite interesting, because you see here first a DC gain, and then the zero is appearing and then going up, and then the pole is actually getting in the picture, and it will also create this flat gain at high frequencies. So this is actually the reverse situation of case 1 up to case 4. So this is of course again a situation where we see that the Miller's approximation is not really valid in this part, because you cannot estimate here the cutoff frequency, because we said this is the upper cutoff frequency. Well, there is not an upper cutoff frequency, it's actually increasing and then leveling up to some value, but these two of course are quite same, so you can almost say that this is a flat line. Again, remember that the Miller's approximation has some shortcomings and also has some limitations, and we see that here in this situation for case 5, where we have a small source and a very small also load resistance. Alright, what's our example? Considering the non-ideal amplifier having a feedback capacitance, and we have used the Miller's theorem to convert this feedback capacitance into two capacitances at the input and at the output, and we have to work out, look at the DC gain, our cutoff frequencies, and we also looked at several cases where we can see that indeed the Miller's theorem gets some Miller's approximation. At some point it's also not valid anymore, as we see it in case 5. If you have any questions about this example, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video.